Now we have the pleasure to receive Peter Wurikti. He's a professor at the Dartmouth College in the Psychology and Brain Science Department. He is actually the chair of the department at the moment. He has prolific production in the field of vision and consciousness. And he's also a prolific author in the field of free will, especially libertarian free will. I'm working under his supervision right now, so it's a pleasure to receive my supervisor as one of the keynote speakers. Please, Peter, feel free to start your talk. The word is all yours. A big round of applause.
Can you all hear me? Is it working? All right. So I'm going to talk about the role of imagination. I'm going to try to talk about freedom at multiple levels, from the neuronal level all the way on up to the level of self-creation. So it's going to be about an hour. Bear with me. Now, I just want to start off with sort of what's going on in the popular press in the past, 5-10 years. These are things that people are actually saying. You've probably seen some of this, like Yuval Harari, organisms are little more than biochemical algorithms. Sam Harris, science reveals you to be a biochemical puppet. Jerry Coyne, we're puppets performing scripted parts written by the laws of physics. There's no end to this kind of stuff, published again and again. Brian Greene is a physicist. We need to recognize that although the sensation of free will is real, the capacity to exert free will, namely the capacity for the human mind to transcend the laws that control physical progression, is not. Our choices are the result of our particles coursing one way or another through our brains. Our actions are the result of our particles moving this way or that through our bodies, and all particle motion, whether in a brain, a body, or a baseball, is controlled by physics, and so is fully dictated by mathematical decree. That's Brian Greene. Here's Robert Sapolsky, who's the next speaker. He said, "We are nothing more or less than the cumulative biological and environmental luck over which we had no control that has brought us to any moment. We are biological machines who know our machineness, and some of us flee from that with responses that are delusional, insofar as irrationally based, confabulatory, and comforting, and some of us face it and feel utterly depressed." So I really find this to be a bleak and actually nihilistic worldview. And they speak as if everybody agrees within neuroscience or philosophy. And many of these people, I don't think have read philosophy very deeply at all. Probably you philosophers would agree. But even within the science, I think they're misguided. So I'm going to just try to create an intuition of why I think they're misguided. So you've all heard of sexual selection, where typically in mammals and birds, the males have some ornament and the females have some criteria for what is attractive. And so if that's big tails, that gets selected for over many generations. If it's giant antlers, you'll end up with the 3.5-meter antlers of the Irish elk that's now extinct. If it is intelligence, you might end up with this as our peacock's tail, with a giant frontal lobes. I don't know if females find intelligence attractive, but it's hypothetical. Okay, so sexual selection is a very fascinating algorithm. Natural selection kind of weeds out the left end of the bell curve. The slow get eaten, the weak get eaten. But sexual selection weeds in the right of the bell curve, the right end of the bell curve, according to some criteria, whatever they might be. Now, if I were to put it into pictures, it would look something like this. So there's an enormous amplification of randomness from the level of gene reshuffling up to the level of phenotypes, and then selection. And then the winners, based upon what the females have selected, serve as the seed for the next generation in this genetic algorithm. And then over many, many generations, you evolve to something with a giant peacock's tail, or whatever it may be. And I want to argue that sexual selection is a useful metaphor for what's going on in the imagination, but even what's going on at the level of neurons responding to their inputs. So let's zoom in on an example. Let's say we want to build a bridge, and here's a picture of San Francisco Bay before they built the Golden Gate Bridge. And so you're faced with a problem, right? And before you go and build any bridge, you have to map out a path in your head about the kind of bridge you want to build. And you might say, well, what are my specs? Well, I've got land on this side and I've got land on that side. I could build it out of wood. I could build it out of gold. I could build it out. And then you say, well, the best option is steel. It's the strongest for the least price. Okay, then it's genetic. Given that it's steel, well, we can make a drawbridge, we can make a suspension bridge, and then over many generations of sexual selection, namely specification in light of criteria, or selection in light of criteria, you evolve in your mind towards some possible solution. So that's the Bay in 1932, and 1952, 20 years later, you had that, right? So they went and then built it. But there were, before anybody started to build anything, this all kind of evolved in people's minds, and they asked lots of companies to generate possibilities. There's the Bay, 1932. This was actually going to be the winning design initially, and then there was an outcry from the public saying, but that's ugly. And so they rejected that and went back to the drawing board. And in the end, the winning design was what you know. And then it's hard work. Given that you've had this internal evolution with something like sexual selection, with criteria, specification, and satisfaction, and an algorithmic or genetic algorithmic evolution towards an adequate solution, then you have the hard work of building it. And that took many years. They started like that and that. So it's not easy, but most of the hard work of this kind of free will happens in your imagination first. The rest is just hard work. And then you have the result, 20 years later, from the initiation of the thought. So a lot of imagination proceeds like this. You're in the present and you think, okay, where do I want to end up in some future? And then you think, okay, that's my end, that's my goal. Then you look backwards from that point and think, what are the steps I need to fulfill in order to reach that goal? And then you set about implementing it. And, I can give you an example from my life. Here I am 33 years ago as a young man. And I was a wild guy. I had studied physics, but I had just finished working in Japan for several years as a businessman. And I said, I want to recreate myself. What should I do? Well, I want to go back into science. And so I had ideas. Here I am in Sumatra. This is where it hit me. I wanted to go back into science. And I thought about what's involved. I've got to study science. I've got to go to a university. I've got to get a mentor. I've got to find money somehow. I don't know how I'm going to do this, but by hook or by crook. And then the rest is hard work. And in my case, I went to night school, and it's Sisyphean. Sometimes you're just pushing around turds, but after 12 years of hard work, I made it. And then I was a professor, right? That is what I think is the essence of free will. It's not arbitrarily picking left versus right. It's this kind of envisioning and then enacting. All right, so here's the talk outline. I'm going to spend the first half of the talk or so talking about causation, mental causation, and causation among and between neurons. And then I'm going to talk about two types of free will, the kind of free will that all other animals who can consider options have. I'll call that a type 1 free will. And then the special kind of free will that we have, which is the capacity to envision a new self and then set about creating that. And then I'll end the talk talking about mastery, how we automatize ourselves to have certain kinds of domains of freedom. Namely, we volitionally choose what shall become unconscious and then create that through practice, including, in the end, I'll talk about the automatization of ourselves, including the kinds of character we want to have. All right, so causation in the brain and mind. So I've called it criterial causation. You can call it parameter causation or boundary condition causation or pattern causation, but they all have basically the notion that we set up constraints which then are met to some degree by subsequent bottom-up processing. So a Newtonian conception of causation, I think, is very inapplicable to the brain, and it's much more Wittgensteinian. So I'll unpack that a bit. So in this book in 2013, I made the argument that Wittgenstein, at least in his later work, hit upon the essence of the neural code in the sense that the neural code is fundamentally criterial, right? So a lot of neuroscientists make the mistake of thinking that causation in the brain is something like billiard balls hitting each other, but it's instead of billiard balls, it's action potential triggering and action potential. But what's missing from that picture, is that neurons can reset the criteria for future firing on other neurons and also indirectly on themselves. So what is Wittgenstein's idea of criteria? Well, it's really his idea of family resemblances. So I could ask some question like, what makes somebody look like a Laplander? And you might say, well, they tend to have dark hair, whereas most Scandinavians have light hair. And I'll say, well, that one's blonde. Oh, okay, well, they tend to be short. Oh, well, that one's tall. Well, they tend to have flat noses. Well, that one has an aquiline nose, right? So there's no necessary or sufficient condition to count as a Laplander. But there might be, say, 10 criteria that when all 10 criteria are met, you'll say that person looks like a Laplander, like prototypically. And he applied this idea to the idea of games and what counts as a bird. But the general idea is that what counts as a member of a set is not defined by Aristotelian necessary or sufficient conditions. It is criteria that are met to degrees. And what you end up then with is an infinite, really, in principle, infinite set of solutions that meet those criteria to various degrees. And it's very fuzzy because that person might meet those 5 and that person might meet those 5 criteria and they might be different. But as a family, they kind of resemble each other. So neurons, I want to argue, are kind of late Wittgensteinian in their function. They set criteria upon their inputs such that what counts as an adequate input to drive the activity of the neuron can be met in infinitely many ways. So you might end up with a neuron that's tuned to, say, a dog. It's a dog detector in the temporal lobes. Well, that neuron will be driven by all kinds of dogs, big dogs, little dogs, cartoon dogs, because they're all adequate. All right. So causation has, as a concept, gone through a kind of evolution itself. Classically, causation was thought of in terms of the metaphor of impact. So Newton kind of thought of it this way. You have A hitting B, and B has no say really in the matter of what becomes of it. It follows in a sense passively. But with the sort of Wittgensteinian notion of causation, B sets criteria or informational conditions upon A for the release of B. So you can start finding very non-Newtonian forms of causation, like, well, if A is striped, I'll do this. And if A is solid, I'll do that. And if it's solid and even, I'll do that. And so you can have all this conditionality placed upon so basically B places conditionality, informational conditionality upon A for the release of some action. And that's what I want to argue neurons do. So let's go look at the history of the idea of causation, right? So initially, the notion of causation was very much driven by this idea of impact. And of course, A must precede B, and B must not happen if A does not happen. Okay, so that's part of the idea of causation, but it's not all of the idea of causation. So let's look at how this idea has evolved over centuries. So in the 1700s, I guess with Newton and so forth, people tended to think of causation as energy transfer with the metaphor of impact. We have people like him, and that's the metaphor in their head. In the 1800s, people started to think of causation quite differently in terms of energy transformation, where now you're talking about chemistry. So it's not about the impact of the energy, it's about transformation of relationships among parts that led to new sorts of properties, such that hydrogen is not a liquid, oxygen's not a liquid, but this new thing can be a liquid. Then later in the 1800s, you had the emergence of thermodynamics, And you're all familiar with this idea that causation is more stochastic or statistical. And but in 1926, 27, you had this real revolution, I think, in how people thought about causation. Here are some people. That's Heisenberg, Planck, Dirac, Einstein, Bohr, and Schrödinger. And they started to deal with really strange things, like the idea that a particle, let's say a photon, or let's say an electron passing through a double slit, whether it ends up here on the photoemulsion or here or here or here, the laws of physics are not violated, right? There's conservation of energy, there's conservation of momentum, but it could end up in different places, right? So the determinism of quantum physics is not a determinism of actual particles, but it's a determinism of a probability distribution, but any measurement could lead to a variety of outcomes, seemingly indeterministically. Okay, so theorists of causation, more recently, people like Judea Pearl and James Woodward, kind of describe causation the way scientists actually do science. They say, you screen off all the variables but one, you manipulate that one variable, and then you look at its effects on some other variable, some dependent variable. And that's kind of what scientists do. We try to do that. And it's sort of, I think, there's maybe a closet Newtonianism in that. There's certainly not a Wittgensteinian notion built into that. But, causation, I think, is not as simple as that. Here's just an example, right? So, you've seen this movie with Harrison Ford, Indiana Jones, and he sees something that he wants to steal, and it's on this thing, and so he tries to put a sandbag to replace it. So the ancient, whatever they were, Mayans or Aztecs, built this trap such that if someone stole that precious relic, these terrible things would happen, right? So it's a kind of trap. But, the ancient Mayans didn't know when that person would come. And it turns out it was totally non-foreseeable. But when the criteria were met for, stealing that thing, this trap was set. In a way, neurons are like that. They're like traps or mouse traps. They're waiting for a very particular set of inputs, a pattern of inputs, and then they fire. Okay. Here's another example from the real world. So there was a cell phone that that the Mossad gave to the bottom ranks of the Palestinian, I think it was Hamas, and they programmed it such that it would blow up. So they wanted to kill this guy who was killing Israelis. He was a bomb maker. And so they fed this cell phone into the bottom ranks. It was programmed like a trap. When this particular number is put in, it blows up and kills him. And so the Hamas bottom ranks fed this phone all the way up. It was deemed to be a safe phone because it had been used hundreds of times for hundreds of phone numbers. But the Mossad knew that this guy had this uncle in Paris, and that they figured out what that number was, and they set it up such that anybody who would call that number, boom, and they killed him. Right? So they parameterized the cell phone as a kind of trap and managed to kill him. So I want to argue that neurons are also they are parameterized, and they can reparameterize each other to respond to this pattern versus that pattern in the future. So I would argue that we need to amend the Pearl and Woodward type of manipulationist or interventionist account of causation by emphasizing the parameters whereby B criterially assesses A, namely B's future inputs. Those parameters can be manipulated with no time constraints placed on when criteria may be satisfied. So this is, I know, a little funny idea, but it's not that Pearl and Woodward are wrong. It's just we need to amend it such that it's not that A causes B and B has no say in the matter. Rather, B is parameterized to have some say in the matter. It says like, well, if this is true about A, I'll do that. If that's true about A, I'll do that. All right. So in the more classical conception of causation, like John Stuart Mill, he argued that a necessary characteristic of causal relationships is covariation of causes and effects. So, a cause and its effects should be essentially temporally correlated, and that's true of the Newtonian conception, but it's not true of criterial causation, right? I put this in here because, yeah, you can have temporal correlation that is not causal, right? Because the sun comes up, which makes the rooster crow. I mean, the sky gets lighter, which and the rooster crows, and then the sun comes up. So I could say, well, the rooster's crowing causes the sun to rise, but I could kill the rooster and then the sun still rises, right? So temporal correlation is not enough. But anyway, Mill's sort of covariation applies to traditional notions of causation, but not to criterial causation, because the timing of the arrival of driving inputs is unspecifiable, like in that Aztec example with Indiana Jones. It could have been 5,000 years before the criteria for what counts as a thief are met. It could have been 10,000 years. All right. So I want to argue that life really discovered this kind of causation, that evolution picked up on this new kind of causation. So criterial causation or parameter causation involves the decoding of patterns that then release patterns. So patterns, for example, of firing that arrive at a neuron, which lead to patterns of firing. And this was discovered by evolution and is the basis of those physical systems that we now call life at every level, from receptors to consciousness. And let me unpack that a little. So biological causation is not Newtonian like this. Rather, B has some say in the matter of A's effects on B, because B places conditions, I will argue, informational conditions upon A. And how this conditionality is physically realized most fundamentally applies in living systems on the phase of energy relationships. Okay, so what is phase? So, you know, in much of non-biological science, we talk about the frequency of energy, the amplitude of energy, but in biology, the phase of energy became extremely important. And what does phase mean? It's a set of relationships among energetic inputs. So one form of that would be shape. Another form of that would be timing. Right? So the idea of simultaneity is an issue of a phase relationship. So in terms of shape, you might have the evolution of a receptor like the NMDA receptor that responds to neurotransmitters of a particular shape. In the domain of a neuron might fire when two or more inputs arrive simultaneously. So the phase relationship it's sensitive to is simultaneity. And, you know, I would argue that these phase relationships don't only exist within the organism, but also in relation to the environment. So for example, a lamprey, if you listen to just a single neuron in, you know, let's say its spinal cord, or even in driving a muscle, you would hear psst, 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 psst. But what allows the lamprey to swim is the timing, the phase relationship. So if this fires, psst, 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 the thing will undulate. And if it's in the right environment, that will allow it to swim. But if it's in the wrong environment, like air, it just flops around. All right. So this sort of criterial assessment of inputs based upon phase leads to certain kinds of what you might call metamers, equivalency classes. So in the case of a serotonin receptor called the 5-HT2A receptor, that's very fundamental in hallucinogens, there's lots of different chemicals that bind to this and lead to hallucinations. LSD, psilocybin, mescaline, and so forth. So you can think of these as equivalent as far as driving that receptor. You know, you can think of a lock, right? And a receptor is a little bit like a lock, and if the right shaped key goes into the lock, it opens. But it doesn't matter what the rest of the lock is shaped like. You just need this key bit to have the right shape. All right. So getting back to Wittgenstein, and there's Eleanor Roche, neurons have some set of criteria that they are placing upon their inputs such that if those are adequately satisfied, the neuron will fire. So you might have a neuron that's tuned to, say, the pattern of Orion, but that can be realized in all kinds of ways. I could put a bunch of lemons on my lawn in that shape, or I can, you know, look at the sky. And so there's infinitely many ways to meet those criteria. It's part of life. Some of the criteria we have are innate, some are not innate, right? So, an innate one probably, at least in my case, would be that I'm attracted to women, right? So if I'm looking for a woman, well, that kind of rules out a bunch of things. I'm not going to end up being married to a tree or a goldfish, but given my criteria, some of which are innate, I nonetheless can meet those in infinitely many ways. I probably also have some sort of threshold. It's probably multidimensional. I might want her to be, kind and smart and funny and well-mannered and pretty and all the, normal things. I don't think I want anything too unusual. And then there's some criteria and a threshold above which I'll say, yeah, that meets the threshold. Now, maybe if I go, can't find anybody, maybe I'd lower my threshold. But this means that there's essentially contingency at every level, right? So you might say, well, why, did you end up with that person? Well, partly it's chance, right? Like you turned left that day instead of right, and had you turned right, you would never have even met them, and you'd be with somebody else now. Now, you were not going to end up being with a dog or a tree, right? So you had your criteria, but the criteria can be met in infinitely many ways. And once they're met, that leads then to choices and commitments, and you decide to have a baby, and that at every level there's assessment of criteria. So then the mother and father who just contingently fell in love and contingently made a commitment to each other decide they want a baby, and then there's an egg in the woman that has criteria for what counts as a sperm, but there's infinitely many sperms that could meet those criteria. And so why did you end up with that baby versus all the other ones? Well, partly it's chance, right? Had she sneezed at that moment or a cosmic ray come down, all kinds of things could have led to a different sperm binding and you'd have a different baby. So it gets back to this claim by Hume that there's nothing betwixt determinism and utter randomness. And that's just not true. There's constrained randomness, which is in between those two poles. And the constraint is specified in your criteria, whatever those might be, and then there's randomness within that. So I can give you some criteria. Think of someone with red hair and you can generate lots of possibilities like Jonathan was talking about. I might say, well, why did you think of, let's say you thought of, I can make it more specific, think of a woman European politician with red hair. And you might say, oh, Angela Merkel. Well, why did you think of Angela Merkel versus Margaret Thatcher? Well, that might just be chance, but it's not utter chance. It's not because it had to be a woman European politician. So there's constrained randomness. So this kind of causation is very central to how neurons work. It's an essential part of the neural code that most people are really not focusing on. So if you look at neurons, it's just mind-bogglingly complex. They're packed so densely together, it seems impossible to figure out how causation works in neurons. And yet, well, if you look back at the history, you had Golgi inventing the Golgi stain, the silver stain, which allowed people to see single neurons for the first time. For some, I think, largely unknown reason, a cell will take up the silver, and if it does, it takes it up everywhere. But most cells don't take it up. And this allowed people to start viewing isolated neurons. And it was especially this man in Spain, Ramon y Cajal, who looked through his microscope for his whole life. Basically here he's a young man, middle-aged man, old man, and he spent his whole life looking through microscopes, and he made these most beautiful drawings of neurons. But I think what's becoming clear is that the neural code is very much centered on not the amplitude of the input, not the frequency of the input, but the coincidence of the input, or the coincidence of the input. So let me try to unpack that a bit. I don't know how to say this. Coincidence is not a coincidence, right? For a neuron, the fact that spikes arrived at the same time is utterly important. It's a central part of the neural code, is this coincidence detection. So how would you try to create information from coincidence or coincidence of action potentials arising? Well, information can lie in a global spatiotemporal configuration or pattern of particles, and importantly, such a pattern is not itself a particle or reducible to particles, right? Simultaneity is not a particle, even though it's realized in particles. A pattern is not itself made of energy, in addition to the particles in which it is realized or supervenes. A postsynaptic neuron may only fire if its presynaptic inputs arrive simultaneously. So really it's a pattern detector. It's looking for a particular kind of pattern, namely simultaneity. And simultaneity is a temporal relationship among particles, but that temporal pattern is not itself made of particles, right? In addition to the constituent particles that arrive simultaneously or not. So a neuron is essentially setting up criteria for firing based upon simultaneity, coincidence detection. So whereas energy or mass cannot be created or destroyed, information is itself not energy, and information has no mass. It can easily be created or destroyed, and this is because information is not realized in the substance of energy per se, but in its spatiotemporal organization, namely its phase relationships, whether shape or timing. So criterial causation is it's a kind of causation based upon pattern, not amplitude of energy, not frequency of energy, but the timing of energy or the spatial relationships among patterns. And this then leads to patterns of output, like patterns of firing, like spiking at a fast rate or bursting and so forth. And top-down criterial causation, I want to argue, is rooted in reparameterization, such that decoders now respond differently to input patterns. So let me try to unpack that. Here's a typical view of a neuron. If you put an electrode into the neuron, you can see that it has changes in potential or voltage across the membrane. And typically, neurons have a firing threshold, and there's an excitatory postsynaptic potential when some, say, an action potential has arrived from the presynaptic neuron. But if you just had an excitatory postsynaptic potential, it will quickly decay. And once it has decayed, it's as if it never happened. So neurons are called leaky integrators. They're trying to integrate over many of these excitatory postsynaptic potentials to reach the threshold, but over time they leak, and they leak for a good reason, namely there's active transport of sodium ions back outside the neuron, so you have a sodium pump. Well, because of this leaky integration, neurons don't have history. They don't remember what happened to them 10 years ago or even seconds ago. So what they're looking for is the simultaneous arrival of lots of these excitatory postsynaptic potentials that will together get them above threshold. This is how you get simultaneity detection or coincidence detection. And you can also have inhibitory postsynaptic potentials. Right. And then if many of these excitatory postsynaptic potentials do arrive at the same time within a particular window, that counts as a coincidence or coincidence that cannot itself have been chance. So there's different ways to accomplish simultaneity. One is synchrony. So every neuron at this level, if they fire together, will arrive at the same time at the postsynaptic neuron and make it fire. So that's one form of generating coincidences, would be neural synchrony. So neural synchrony is almost surely a very important part of the neural code. But there's another way to generate simultaneity, and that is for one single neuron to fire like crazy, really fast. So if the integration window for what counts as simultaneous for a pyramidal cell is typically, say, 25 milliseconds, if this neuron fires alone, 7 times within 25 milliseconds, that might drive the subsequent neuron. So again, in addition to synchrony, bursting is also likely to be a very fundamental part of the code, the neural code, which is itself based upon coincidence detection. So really, coincidence detection is at the heart of the neural code, and which is in turn set up to realize a type of criterial causation, a sensitivity to certain patterns of inputs. So let me try to unpack that. Yeah, so like dendritic coincidence, you can have a kind of neural code that is based upon truth conditions being met among different dendrites. Let me give you an example. If a spike arrives at this dendritic branch at the same time as this dendritic branch, then these will both depolarize, and that if both are the case, then this next dendritic branch might depolarize. So there's a kind of if-then statement that's dependent upon simultaneity. So these dendritic branches can function as logic gates, and you can create combinations of these, and you can create a quite complex set of conditions such that if this is true and if that is true, then, and also if that is true, but that is not true, then I will fire. So a lot of the neural code might have nothing to do with action potentials. It might be a dendritic code, right? So the action potentials will then only be telling other neurons the conditions for my truth conditions have been met. You know, I'm a dog detector and I have found the conditions that define a dog. Those criteria have been met. I fire and I tell other neurons, there's a dog out there somewhere. But the actual computation was a dendritic computation. So you end up with these neurons, you know, here's some temporal lobe neurons that seem to have very specific tunings. So here's a neuron that Charlie Gross at Princeton recorded from. And that histogram at the bottom is firing rate, and the black bar at the bottom is when the face was presented. So this neuron in the fusiform face area likes A, it likes B, but it doesn't like C, doesn't like D, it doesn't like E either, certainly doesn't like F. But G is okay, but H is not. And so you might say, well, that's a little strange. How do I know what's actually out there if this neuron has fired? I mean, well, maybe you don't, right? So this neuron is creating an equivalence class of all the things that make it fire. Why? Because they have met its informational criteria for what counts as a face, which in this case seems to be something round with two black dots and a mouth-like thing. And if those criteria are not met, sorry, the neuron doesn't fire. So some lovely work was done by Quiroga, Itzhak Fried, Christoph Koch, and they found that some neurons seem to respond to, in this case in the hippocampus, to Jennifer Aniston. But, you know, what is it about all those, what makes Jennifer Aniston? You know, what makes anything? Some criteria had to be met, and the neurons seem sensitive to that. And they have continued this work and have found what they call concept neurons, and they're really amazing, right? So there are these concept neurons that respond, say, to Oprah Winfrey, and they will fire seemingly indistinguishably if the patient is shown a picture of Oprah Winfrey, or her voice is played, or the name Oprah Winfrey appears, the neuron goes brrr, right? So that's pretty abstract, and yet those things seem to exist in the hippocampus. All right. So neurons are coincidence detection systems at every level, from the level of NMDA receptors to dendrites to across dendrites and neural circuits, right? Because the causation is looking for the fulfillment of informational criteria based upon simultaneity as a pattern. And this fact allows neurons to realize both logical operations and criterial assessment of their inputs, and that these criteria, moreover, can be changed dynamically. So neurons not only make other neurons fire, they can reset the parameters or criteria for other neurons' future firing, and this accomplishes a resetting of the informational criteria that must be met by future inputs to the that could trigger action potentials, right? So a neuron that's tuned to a dog could be reset to be a neuron tuned to a cat because you change the criteria. So the neural code is not just a spike code. It's also a synaptic reweighting code. In other words, information is not only realized in action potentials, information is also realized in the slow and rapid reweighting of synapses. So this is really tricky, right? It's a little bit like yang and yin. You need both yang and yin. So the yang of the neural code is action potentials, but the yin is the rapid synaptic reweighting that leads to the interpretation of action potentials. Have they met my criteria or not? Okay, so let me look at the whole brain now for a second. If you open up a brain, you see all these tracts, and people have labeled them. And this has led to a whole field of, diffusion tensor imaging and connectomics and so forth. And it's led to a kind of bad metaphor. I think, the human mind is very metaphorical. We're driven by lots of bad metaphors. One is that the brain is a computer, which it's not, right? No brain rewires itself on a millisecond time scale. There's no hardware-software distinction in a brain. And if there were, I would download Arabic, speak it tomorrow. There's no consciousness in computers. Another bad metaphor is that the brain is like a highway system, when it's just not, right? Somewhat better would be to view it more like this, where synaptic weights now will play the role of these shunts, such that a neuron under one set of synaptic weights will talk to this neuron, but under a different set of synaptic weights will talk to that neuron. To make it metaphorical, I can, connect train tracks, this way from, let's say, New York City to San Francisco. I could also create a path like this, and there's a little bit in the middle where it's the same train tracks. So are those train tracks part of a circuit that connects New York to San Francisco, or New York, so there's many different ways to connect everything with everything. And I want to argue that neurons themselves are multiplexing in this way through rapid synaptic weight changes. So we really shouldn't talk about neural circuits. We should talk about neural epicircuits that change on the fly. So that might also be a basis for representation of information in the brain. Okay, so again, the neural code is not just a spike code, it's also a synaptic reweighting code. And just to give you a sense of the importance of having both yin and yang, if I were to measure only the energy passing through the system, let's say I were to measure your voice box, what I would get is but in addition, I need the filtering imposed by the change of shape of your mouth. But if I were to only measure that, you would get this. So you need the dynamic interplay between the energy passing through the system, the action potentials, and the rapid filtering imposed by rapid synaptic weight changes. Okay, so we have to start thinking, I think, beyond action potentials. We have to start thinking about the neural code as involving rapid synaptic weight changes, and that a lot of the computation is happening inside the dendrites before any action potentials are happening. Okay, so I'm going to stop talking about causation in the mind and brain, and I'm going to talk now about freedom among minds or animals. So here, what do I mean by second order free will? Let's talk about first order free will first, right? But second order free will is the idea that you can choose to become a new kind of chooser in the future. I would argue that no other animal does that in any kind of cognitive way. No animal says, next year I want to be a different kind of tiger, one that eats fewer tapirs and more pangolins. They just don't do it. We can do that, and I want to argue that's because of our wild imagination. Okay, but let's just, unpack these different notions of free will. One is this notion of proximal free will. One notion of that would be picking, where, it doesn't really matter which apple you pick. They're all equivalent. Another might be choosing, where you're kind of trying to choose among things that are more or less equivalent but different, like types of milk. But then there's this more interesting form of deliberative or distal free will that is playing out over long durations, in which we strive to fulfill some long-term goal. And that's mainly what I'm interested in. This kind of creative planning, in which we envision a future that we want to accomplish, and then we carry it out step by step, despite setbacks. For example, when I decided I wanted to become a scientist, I said, okay, I've got to get into a grad school. And then I went and I tried to work in someone's lab, and they said, forget it, who are you? And then so I picked up and I went to another lab, and they said, oh, I'll give you a chance. Right? So despite setbacks, because I had this goal, I was very teleological in my behavior, and through great striving, I was able to make it happen. Okay, so what's first order free will? I gave this example a couple of years ago here, right? What do we mean by a first order free will? Well, how's this as a definition? If a mind can alter the probabilities of future events for its own reasons, and if it can knowingly choose among alternatives, some of which might really happen, then we can say this mind exhibits free agency or has free will. And I would say that a jaguar has that, right? A jaguar can have a goal of catching a capybara, and it has in its head a kind of, if I go that way, it's slower, but it's quieter. But if I go that way, it's, faster but louder. And the capybara also has a tree of a branching Borges tree of possibilities in its head. And then the jaguar commits to a path, and things play out as they do, and then it kills, in this case, the capybara. So I think a lot of our subjective commitment to a libertarian free will comes from the subjective phenomenology that we have a branching set of possibilities in our imagination. Now, it's very important, I think, that those branching possibilities correspond to the branching possibilities open in the world. And so then that gives rise to a problem that, we might have delusions about what's really open to us. So it's important to have a free will, to have a realistic assessment of your mapping between your imagination and what could really happen. Right. So, what we imagine affects what we do, and this in turn will affect what then is open to our imagination. So there's this dynamic cycle between imagining what is possible, doing this, and getting feedback, and then reimagining, and so forth. Okay, but type 2 free will, I think, is unique to humans in that we can imagine things that a jaguar or tiger simply cannot imagine, right? The life of a jaguar is the same as the life of a jaguar 10,000 years ago, 1,000,000 years ago. It just, because they're much more driven by instinct, whereas we have the capacity to imagine things that are counterfactual, including concerning ourselves, some of which we can make happen. Right? I don't speak Swahili now, but in a year, if I studied hard, I could probably do it, right? And I have a lot of possibilities open to me. And so the human imagination is really unlike, I think, the imagination of any other animal, and this gives us this incredible freedom, right? And it can set us free in both good and bad ways. But what do we mean by imagination, right? As opposed to just mental imagery? Well, imagination is not simply imagining nouns like faces and houses and so forth. It's very much dynamic. There are verbs of the mind, like mental rotation, putting things together, taking them apart, and so forth, that allow us to operate upon the operands of our imagination and create new things. I'll give you an example. Right, so imagination is operations, especially there are non-volitional variants, but there's also volitional variants of operations over operands in our internal mental workspace or virtual reality. And one question is why the imagination has to be conscious at all. Well, I would argue that consciousness is the domain of operands that we can volitionally operate over. So there's this one version of that would be volitional attention. Anything that you can volitionally attend, you're conscious of, and anything you're conscious of, you could volitionally attend, right? So anything you're attending, you're conscious of. Anything you could attend to in the next moment, it could be part of the conscious background. So there's this deep link in waking consciousness between what is attendable or attended, what is experienced, or and then what is volitionally operatable upon. I would say the imagination affords volitional operations as well, and this is probably linked to why it should also be experienced, so that we can play out virtual realities in our head to see how it feels. Otherwise, if it were not experienced, we couldn't experience how it feels, and it wouldn't help us make a decision. All right, so here's a good example, right? So these two men, Orville and Wilbur Wright, were just bicycle repair shop people in 1890. And they said, we don't need to build an ornithopter that flaps. We can create something new. And so they had it in the mental operations of their head, of their imagination. They said, what if we put a propeller up front and attach it to a wing and suck the thing forward? That might work. So here they are in their bicycle shop in Dayton, Ohio, and they just did it again and again. They didn't give up. They made lots of mistakes. I mean, people were getting really badly hurt, jumping off of cliffs and so forth. But eventually, they got to a point where the crazy thing kind of stayed aloft. And here it is, Kitty Hawk, 1903. This is the big moment. And that changed the world, right? So acts of mental operations, putting a propeller onto a wing in your head, and then just not giving up and trying to create the damn thing, led to this, which then led to this, and more mistakes, led eventually to these newer models, led to this, led to this, led to this, and now we live in this crazy world 20 years later, that is utterly transformed by this act of imagination that these two bicycle repairmen had. And their imagination changed reality, right? But the hard work of their free will was happening in their free imagination before any action in the world. So we shouldn't conflate free action with free motoric action. Even if you have locked-in syndrome, you can choose to volitionally attend to the radio, or volitionally attend to the TV, or volitionally attend to your memories, right? So the freedom of motoric action is downstream of the freedom of the volitional operations, some of which happen in imagination. But I would argue that this kind of these mental operations also led to kind of a potential for madness amongst us. So in the second book, I make the argument that something happened in our brains that led to a kind of demodularization of mental operators. The ability to apply operators where they did not evolve to operate. And that this has given us both an incredible freedom, but also a form of madness. So for example, take a sexual fertility operator that likes redness and symmetry. Well, now this promiscuous operator can be inappropriately applied to a sunset. And this could be the birth of art. Prosody could be, that evolved to process language, now is misapplied elsewhere and we get music and so forth. So I won't dwell on this point too much, but I do think that the form of our imagination in part emerged through a kind of demodularization or promiscuity of operators. And so, another part of it that I won't get into too deeply is that our consciousness seems to be bifurcated in a way that of a tiger is not. Right. So in addition to the perceptual consciousness that we have in common with a chimpanzee, we have on top of it this level of narrative that's explaining what's going on, which can lead to amazing things that are correct, but it can also lead to terrible things that are incorrect. Let me give you an example, right? So if a lion comes across a bunch of zebra hoof prints, I can tell you what it will do. It will do nothing, because it doesn't look like a zebra, it doesn't smell like a zebra. But our ancestors reach a point where they're like, aha, well, there was about 7 of them, and they were going in that direction. It's about 2 days ago, and they're probably going behind that mountain and going to that imagined savanna there, right? So you can see how even though physically we're weak in comparison with a lion, this intellectual capacity to imagine on the basis of the evidence led to, in this case, something correct, which would give us an advantage over lions in hunting. But that same capacity to see the invisible and create it could lead to madness, right? So then, let's say it hasn't rained in 4 months, and people might then project their, intentionality operator upon the sky and say, well, therefore there's a God who's angry at us, and therefore we have to appease the God and throw a baby into the volcano. That's kind of insane, right? So we're kind of this, it's the same capacities that make us so crazy also give us our power. So really the question is, how do we harness this fire of our imagination so it keeps our house warm and doesn't burn our house down? It's a huge problem. But this capacity to imagine what doesn't exist led to this 30 to 40,000 years ago. But it also leads to many forms of madness. So just to finish that section, I would argue that the imagination, in the case of humans, emerged through a kind of demodularization of operators that would be modular in a chimpanzee. And this disencapsulation of previously encapsulated operators led to all kinds of things that we do that chimps don't do, like art and music and so forth. And some forms of our imagination are volitional, and we can choose to apply an operator in our working memory and do something like attach a propeller to a wing and then play it out and say, well, maybe that would work. And this kind of design enhancement of consciousness allowed our hypotheses to die in our stead. We could have this internal virtual reality where we could play things out, try things out, and then, if they seem plausible, go in and enact them. Okay, so now I want to go to the second, I guess the last third of the talk, in which I talk about mastery. So what is mastery? Well, part of it involves forming a vision of what you want to become. So I might say, well, I want to learn the piano. Well, I don't play the piano. How can I get good at piano? Well, I can do things like get a book or get a teacher, and I'll practice. And in the end, I can automatize certain abilities. Things that initially are very challenging, like I'll say, okay, those 3 or 4 dots, that's a C chord. But with practice, that becomes automatized. I can automatically see that as a C chord. I can transfer that automatically to this. So that would be chunking. And then I can create chunks of chunks. So maybe this sequence, boop, 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 becomes a unit. And so masters, I want to argue, play a role in their own automatization. They choose volitionally, initially, I want to automatize that. They practice it. It becomes a habit. And over time, this can lead to a form of mastery, whether playing the piano or mastery even over your own mind. So, for example, in music, I'm not very gifted in music, but I'm very determined, and so I was given a very small amount of potential genetically, but I was able to become competent at music through hard work. Other people, like Mozart, have a huge potential, but had Mozart not focused on realizing his potential through practice, he also might not have realized his potential, right? So, this notion that everything's genetically given, I think Sapolsky is going to say stuff like this, I think it's just incorrect. What's given is not an outcome, but a potential, and how that potential will be realized depends on the environment, of course. Of course, socioeconomic status influences our life outcomes, but we ourselves are part of the influences upon how our potential will be realized. I could say, okay, I'm going to learn the piano, or I'm going to learn the guitar, and then I set about learning it, chunking it, and at the end of 10 years, I can play the piano. So our own decisions are part of the environment, actually, that will influence in which direction our potential will be realized. So, I guess I want to argue that free will is really fundamentally a matter of our free imagination, at least in the human case. But starting with an imagined vision, we can shape the future to realize that vision, and sometimes it takes years and years of hard work. So it's the same capacity that leads us to be able to imagine this, or this, that also allows us to imagine this, or this. So again, we have this incredible capacity to imagine counterfactually, sometimes volitionally, combining things and creating a future which we then can strive to realize. And it's up to us to realize the future that we want, right? We don't have to. One thing that really bothers me about these sort of people who say we have zero say in the matter of what we become, that we're just biochemical puppets, is, the world is full of nuclear weapons. What, are you just supposed to sit down and accept that? The world is full of injustice. We should just, we're just puppets. Not my fault. I can't do anything. I think it's BS. It's wrong. We can make a difference in this world. Okay, so then I want to talk about how we automatize ourselves and become masterful. This is really Aristotle's 2 minutes? Okay. So Aristotle's Nicomachean Ethics, virtue ethics. So again, I can say, okay, I am not, I'm a very flawed person, but I want to really work on some aspect of myself, and I can set up a plan to accomplish that. This is at the physical level. I can say, well, I want to become more fit, and I then just go to the gym and work out. Now, I can't grow wings because that's not within my potential, but within my potential, I can realize a lot of things. I can learn a new language. Here's a study that we did in which we had people learn Chinese for 9 months, intensively for like 5 hours every day, and we looked at the changes in myelination. So learning is one mechanism whereby we change ourselves, and so these people at the end of 9 months could speak Mandarin adequately. Okay, so let's look at some real masters, right? You have Vladimir Horst there, you have Michael Jordan there. They didn't come to the world being masters. They were babies, right? What led to them becoming masterful? Well, I guess in one way they might have started out just realizing they were incompetent. And then they realized, okay, I got to do something about it. I'm going to practice and practice. And eventually they automatized a lot of things that they chose to automatize. So there's volitional choosing, but then it becomes non-volitional automatization. Okay, so I have 2 minutes? Okay, I'm going to skip all this. So bear with me. Okay. Okay, well, I was going to go through a little bit of science, but so volitional attention seems to be a really key operator. One of its roles is that it glues things together, metaphorically speaking, and that is a glue that can then harden. So even though I can choose to, through practice, attend to these 3 black dots, which eventually become a unit because I've attended to them, that hardens and becomes a chunk in my memory. This becomes a unit. I can have chunks and meta chunks and so forth. I can have sequences becoming chunks. A big part of mastery is what you choose to automatize using volitional attention, the glue that can harden. And so people come to master different things, right? Some people will become neurologists, some people will become, whatever, because they volitionally chose to become non-volitional in a way that they wanted to. They automatize themselves. So this kind of chunking affords mastery. So I'm going to skip all this because there's no time. Sorry. Sorry. There's just no time. This is some science, but it's just making the point that we can chunk ourselves. Okay, let me go beyond this. So, people talk about habit formation. Well, we can volitionally choose to create automaticities. And central to this are the basal ganglia, where things that were attentionally demanding, become effortless. And so this is very central to mastery, I would argue. So we can turn our intentions into habits, and can be, this can be our best friend if we use it wisely. Right? I mean, you could also automatize things that are terrible. And any of you who have learned an instrument or a sport will know how awful it is once you have automatized a mistake. It's much harder to undo a mistake. This is why coaches and teachers and friends and parents are so fundamental to our development, because they help us automatize correctly. So we should not be alone. Really, our volition is the result of a community. Okay, so... right, so we automatize ourselves by volitionally choosing to attend and practice. Okay, so to make it consistent with the Nicomachean ethics, we can also automatize to some degree our character and even our decision making, right? So it's not that we're robots, because we play a volitional role in setting up our unconscious robots, right? We choose to automatize decision making in a hierarchy of decisions, and in a way, decisions are hierarchical within us as well. Many of these at the lower level are automatized, although initially they were not. So we're in a way a little bit like Napoleon, right? So Napoleon had the feeling that he was in charge of his military. If everybody obeyed him, he felt like I have a free will to invade Minsk. But that decision to invade, Minsk, required lots of lower level agents to fulfill that, right? So, and decision making is happening at every level. At the bottom level, there's a soldier who has a kind of agency. Like I got to shoot that Russian soldier versus that Russian soldier, and that decision making is not happening at the top level of Napoleon. So Napoleon's feeling of free will over his army depends on agency at multiple levels. And so we have a lot of mid-level agents that go into our life, many of which we have then automatized. And if you have a renegade general who doesn't obey Napoleon, it would seem to Napoleon that he has something like alien hand syndrome. So I think a very interesting problem in free will that I have not seen philosophers address very much is the automatization of mid-level agents that we initially choose to automatize. And sometimes we automatize things maybe unwisely, right? A lot of American soldiers are playing video games all the time, and they essentially become trigger happy, and this has led to an epidemic of Americans shooting Americans. They call it horribly friendly fire. So then that's an interesting moral question. If somebody has wired up an automaticity like shoot when in doubt, where are they responsible? Well, it was an automaticity, but it wasn't initially an automaticity. They practiced it. Anyway. So we're able to will the nature of our future consciousness, I would argue, and we can choose to automatize whatever we want that lies within our potential. And by automatizing what we choose to master freely, we are freely willing the future nature of our own consciousness. Okay, and let me see, I've got too much, I know. I will stop there. I just want to emphasize again that, my point to Jonathan is that there's this beautiful interplay between volitional conscious operations and then what is going on unconsciously, and then it's not a linear causation. They're talking to each other. One of the most important is what we choose to make unconscious by practicing it. So you might say that our unconscious is almost like a fossil collection of all of our past volitions, things that we automatized. And thank you for your attention.
Well, thanks, Peter. So questions?
Hi, thank you for your talk. About the first third of your talk, when you talk about coincidence, how would, considering that each neuron receives many synapses, how can a neuron differentiate between what it would be a signal and what would be a noise, so as not to mess up the coincidence that detectors?
Exactly, yeah. So neural firing is extremely noisy. So neural firing is extremely noisy. If you take a neuron and you give it identical inputs, as far as we can tell, it's identical in every way, the neuron will fire very differently, So it typically follows what's called Poisson statistics, but it's very variable. So you might say neural firing is very noisy. It's full of randomness. So the way that a postsynaptic neuron seems to distinguish signal from noise is that which is simultaneous, right? Things have to arrive at the same time, and then that counts as real and not just noise. So simultaneity, whether through synchrony of the previous level or bursting of the previous level, rises above the noise because the coincidence of spikes arriving within the small window of decay imposed by active sodium pumps leads to that cannot be a coincidence. So coincidence is not a coincidence, is how neurons say that is not just noise.
Hi. I know that all of this gets harder when we grow older. So how can we deal with it? Like every time I think I kind of lose hope sometimes because I think no, I'm getting older, so it's getting hard. So how can we deal with the fact that our brain um, just get old?
Microphone. It's directional microphone. Just
Okay.
we're talking out to the microphone.
Can you hear me now? Right. So there's many ways to maintain your plasticity. One of them is simply to pay attention. By paying attention, you basically you learn what you pay attention to, and if you don't pay attention, you know it's as if it doesn't even exist, right? We live in a world in which there's constant distraction, and we even have these weapons of mass distraction in our pockets. That's undermining our ability to learn what we want to learn. Another aspect is curiosity. So we've done studies in which we have shown that there's a part of the basal ganglia called the caudate, and it gets lots of dopaminergic inputs, and people really differ in the volatility or the degree to which their circuitry is affected by a positive input. So some people in the bold signal we saw would go up to like 0.5%. Other people go up like 5%. And so we noticed that people seem to differ based upon how rewarding they found things to be. So imagine, who would continue to learn more? You have two people who are identical in intelligence, but one of them, they learn something, and they're like, eh. And the other person's like, wow, that's crazy. Who's going to learn it better, right? So part, I think, of learning is not just attention, but maintaining your curiosity and enthusiasm, right? Little children are very enthusiastic and learn crazy amounts of stuff, right? And they're kind of shut down by the world, So a little child will say, Mom, look, this tree has white bark. Yeah, it's a birch tree. Okay. Mom, this caterpillar has red eyes. Mom. Jimmy, I'm busy, right? And so the kid starts to lose his enthusiasm and he becomes ossified. And then there's lots of ways to maintain your plasticity. A kind of risky one, but one that I think is very potentially powerful, is taking psilocybin. So there's a scientist. So I'm collaborating with the group at Johns Hopkins, and they're the real leaders in this. But there's a scientist there. Actually, she just moved to Berkeley. Her name is Gould Dolan. She makes the argument that psilocybin puts the brain back into a critical period, and this is potentially very powerful. So what do we mean by critical periods? So let's say I wanted to build a new university, and I didn't know where to put the sidewalks. So I just covered the fields with grass. Everywhere has grass, and I say, okay, new students, just walk everywhere. And then the trails form because they walk the best paths. Then I say, okay, I'm going to put my sidewalks there, my concrete there. Evolution created this kind of mechanism where, for any given ability, mammals have a critical period in which they play a lot. And so they're forming these paths, and then as the critical period closes, these paths are set. And actually it involves the NMDA receptor, actually the replacement of one subunit of the NMDA receptor with another, and then you're set for life. But what if you have learned some dysfunctional path? So say you're a girl who has come to associate the violence of her father with love. Then for the rest of her life, she has this connection. That's dysfunctional, right? What if you could go back to the period of grass and learn things better, right? Now, there's a real danger in taking psilocybin or mescaline or LSD or San Pedro or all these chemicals, because what if you take them and your mentor now is some psychopath like Charles Manson, and then you reform a path to worship Charles Manson. So this is why this also has to be done with real wisdom. But I think it's potentially very transformative in maintaining your plasticity. Okay, maybe I should have talked about that because it's illegal, but anyway. Good. Yeah. Well, yeah. Her and then Eddie.
I just want to hop on the psychedelics train a little bit because I've been reading that there's a real push towards the use in industry, pharmaceutical industry, and there's an attempt to isolate some compounds. I don't think it's exactly psilocybin, but something to allow the changes in neuroplasticity without the trip. So it would like dispense with the talk therapy and the whole setting. So do you think that's possible? Do you think without the second layer of like the changes in the narrative, there could be the same effects or comparable effects?
Right, so the question is whether the conscious experience associated with hallucinogens is necessary for their transformative effects, like becoming less depressed. I mean, it's probably the biggest effect size in all of psychiatry that one shot of psilocybin can lead to greater openness in your personality and less depression for multiple years out. So, but was the trip, the conscious experience necessary or not? I think the people don't know. So my colleague at Dartmouth, Kate Naudial, is doing an experiment in which she gives rats psilocybin either when they're conscious, or she anesthetizes them and gives them psilocybin, and then she measures the degree to which they're afraid to go into a field, or so we'll see. Now that you might have antidepressant effects in a formerly anesthetized rat that didn't have the experience doesn't mean that the psychological experience also didn't have causal effects. I mean, I think especially in humans, if you have an experience like I met the Earth Goddess Mother lizard or something, well, that might have an effect that's above and beyond the neuronal effects, right? So humans are complicated, yeah. But we don't know. It's a wide open area. Okay, Eddie, let me have it.
No, this is mostly just a comment that that discussion of the imagination in the free will literature is almost nil, and that's a big mistake because it's clearly crucial to the type of free will that humans have. But the comment is just, it was interesting that you didn't need to bring up indeterminism anywhere in your talk. I mean, you did once, but it was completely unnecessary, because the whole point is we have this capacity to imagine alternative futures. It doesn't matter whether each of them is open in some ontological sense, because we are the ones that cause one of them to become actualized only by imagining it among alternatives. So I think it's completely compatible with a compatibilist picture. But either way, I mean, I don't really care. If you want the indeterminism, that's great. It doesn't require anything more than indeterminism. There's no agent causal powers or anything. It's what's crucial is our conscious imagination of future alternatives, figuring out how to get to one of them, and then that being the cause of what becomes actualized if things work out right and we work hard enough.
Yeah,
so
and
it's just a beautiful account.
And we're very cybernetic in the sense that we have some goal. Like I wanted to become a scientist, and I had endless setbacks. I ran out of money, I got fired, but I was able to, that song, I get knocked down, but I get up again. And so then I was like, you know what, screw it, I'm gonna try again, and that makes a difference in what actually happens. Now about determinism and indeterminism, I'm so puzzled why people expend so much energy on that, when I now think it's simply not settlable for a very concrete reason. From within any finite subset of the universe, like a brain, there will be influences coming in, like cosmic rays or something, which makes activity within that subset randomized, and that's true of every subset. So the only way to know if there's determinism or indeterminism is the level of the whole set, which is the universe. The problem is that we're part of that. And therefore, it's a Gödel problem. In order to know whether the whole universe is deterministic or an indeterministic, you would have to know the basis of your own knowing. This is a Gödel problem, and therefore I think it's not settlable in principle. Well, if that's true, well, then either way, it's a leap of faith. You can take a leap of faith to determinism, a leap of faith to indeterminism. So that's my bias.
No. Just if you're interested in this or anybody else's, Janin Ishmael has wonderful views about how to understand this paradox of self-knowledge and how to understand it in a deterministic framework, but it doesn't really matter, again, which way you go.
Great. Well, we have 7 minutes, but Thomas, you can ask them. Okay, who is next?
Let Thomas, you have the mic there. Just let Thomas.
Sorry. Who's next? You?
Professor, first,
Call
thank
me
you.
Peter.
Okay, Peter, thank you so much. Did you? I'm so happy. There was one thing, though, you said that made me really, really sad, which is about the brothers, right? I'm so sorry to tell you, but 2 years before them, a Brazilian guy flew in France. So that's a discussion we can have later. But
you're a radical nationalist.
But actually, I got interested in the randomization that happens within constraints. Could we think of that as like levels of free will, like limitations on our free will?
Well, sure. Some people are are much more constrained than others. Like an addict has very few options open to them.
So those constraints would.
I mean, you can be so constrained that it is as if you have no free will. Like if you live in a prison in a totalitarian regime, and that's, I guess you still have the freedom of your imagination, but you're so constrained as to, But I think most of us in this room have a lot of possibilities open to us, and we can choose to do all kinds of stuff, live in different countries and learn new languages, even become new kinds of selves. Within limits, right? I mean, you cannot grow wings, and but you can still do a lot.
Okay, great, and the last one.
Thank you for your talk. My question was just, for you, imagination, do you have an internalist conception of imagination that happens in the brain, in the mind? Because when you compare with mental imagery, the first thing that I thought, well, mental imagery is internal to the mind, but imagination, especially tied to creativity, I will think that it's something much more inactive and embodied, that it's like you do something, you come with an idea, do something, you imagine something, some other possibilities, and the way that you present it made me think that you were having this internalist conception of imagination, but I'm not sure if I'm right.
So I completely agree that our imagination is a kind of embodied cognition. So we did a study, an MRI study, in which we had people imagine rotating things this way, this way, this way, or this way. And then we also physically had them rotate 3D printed versions of the same thing, this way, this way, this way, this way. And then the question was, can we use the motoric decoder, classifier, to decode the imagination or vice versa? And in a lot of these supplementary motor areas, you could, which suggests to me that the operations that we carry out in our internal virtual reality are actually ones that we learned with our body, and that we are applying with virtual hands and virtual eye movements, but over a virtual body, in a virtual reality, manipulations. But if we didn't learn it through our body, we couldn't do it. I mean, one danger, like any of you who have not yet had children, if you do have children, don't let them spend their lives doing this. they should be outside playing so that they learn how to use their body, because that will affect their imagination later. Now, let's say that you have a cow, right? Like, what kind of imagination does a cow have? Well, I don't know, but it would be a very tragic cow that could imagine manipulating all kinds of things in its working memory, and then it says, oh, I want to make it realize in the world, I have a hoof. I can't do anything, right? So my guess is cows don't imagine manipulations like we do, because a lot of our manipulability comes from the manipulability of our hands, and then we have internalized that. Yeah. So it might be actually that the origin of the human imagination is rooted in the emergence of our hands. So. All right.
Big round of applause for Peter Urikti.